Today I'm at the Thomas J. Watson Research Center in Yorktown Heights, New York. This is the headquarters of IBM Research and also the beating heart of IBM's quantum innovations. So what that means is that here they make really cool stuff like the thing behind me, a quantum computer. Very simply put, quantum computers harness the wacky principles of quantum mechanics to potentially perform things that's unthinkable for even the best supercomputers of today. And that gives them a wide variety of future applications, like extending the life of EV batteries and advancements in medical and basic science research, and just whatever extremely complex problems that humanity decides to come up with in the future. But really, the most exciting thing about quantum computers is that they're here today, now, and you at home, can connect to a quantum computer for free. No PhD required, probably. We're gonna do something with IBM's quantum computers today. So what are we doing and what are we using?
Right, so we're looking at what's called a quantum magic 8-ball.
Okay.
So let's say you had a question in life to which you wanted the answer, but you were indecisive. There was 8 possible outcomes, and you wanted a magic 8-ball to just pick an outcome for you at random.
Okay.
Quantum computers are very good at generating genuinely random distributions, something that classical computers cannot do. And it's one of their strengths. It's used in applications like cryptography, simulations of physical systems. But here we'll just use it to sort of resolve our own conundrum. So imagine if I had a question that I wanted to address, like, is my flight going to be on time on a certain day? And there's 8 possible outcomes that you see here. So, yes, not today, definitely, try again. Signs point to yes, not likely, sure thing, outlook not so good. We can actually encode these outcomes into the set of results that you get from running a quantum computer. And that's what we'll do in this demo.
Right, and we'll be using something called Qiskit.
Correct. So Qiskit is IBM's SDK, or software development kit, that we use for running quantum circuits on IBM hardware and building algorithms as well.
Okay, cool. So let's get started.
Sure. This cell does the job of installing Qiskit,
Okay.
Which is what you just referred to.
Right.
And then here we install Qiskit IBM Runtime, which is IBM's client for interacting with IBM's quantum hardware.
Okay.
Then I've created a list that encodes the possible outputs that we just discussed. Okay, so now we're going to create a quantum circuit, and maybe what I'll have you do is code it up.
I have very marginal knowledge of Python.
It's all good. It's all good. As you'll see, it's very, very easy. It's just a few lines of code. You can go from there. So let's create a cell. And maybe what I'll have you do is do from Qiskit. So Qiskit is IBM's SDK, as we discussed. Let's import quantum circuit. And quantum circuit is basically the skeleton on which you will build your quantum circuit of interest that you will run on IBM backends. So let's press enter.
Enter.
And what we'll say is QC, call it variable QC equals quantum circuit. And square brackets. So let's do square brackets, real ones.
The other one?
Yes. Yeah.
Okay.
I got it. So 3.
Yeah.
Now 3 here represents the fact that I'm creating a 3-qubit circuit.
Okay.
And why that is when I have 8 possible outcomes, I need 2 to the 3. So basically 8 is 2 to the 3.
Right.
And what that means is I need 3 qubits to encode 8 possible outcomes.
Okay.
So that's why I picked the number 3 here.
Okay.
So this is now set up an empty quantum circuit for me that has 3 qubits and nothing else.
Okay.
Let's now start adding operations to it.
Sure.
And it's, as you'll see, very simple. So let's do something along the lines of, let's do QC dot H and acting on 0. Exactly. So this H is the Hadamard gate.
Okay.
And what it does is it puts my qubits into a state of superposition.
Okay.
Right? Superposition is a term you may have heard a lot about. And basically all that means is my qubit is in a state where if I measure it with 50% probability, so sampled across a bunch of measurements, I'll measure 0 50% of the time and 1 50% of the time. And this gate actually does the job of preparing that state. It's called a Hadamard gate, and here it's represented with just a simple H.
Okay.
So we've put a Hadamard now onto our first qubit. So instead of counting as 1, 2, 3, we're counting 0, 1, 2.
Okay.
Now let's go to the next line maybe and do QC.H1.
So that's our second qubit.
Correct. And let's do something similar for the third one as well.
Q.H2.
Exactly. So this has now taken my quantum circuit and added 3 Hadamard gates to it.
Okay.
We'll visualize that in just a second. But before that, because we are interested in measuring this quantum circuit or sampling from it, let's add a line and let's do QC dot measure.
Measure.
Measure
Measure.
active.
Active.
So it's
Active.
and let's add parentheses.
Parentheses.
Exactly. So this is going to add measurements to these qubits.
Okay.
And let's go to the next line now. We're ready to draw it out. So let's do QC
QC.
dot draw.
Draw. Okay.
Yeah. And parentheses
Parentheses.
and quotes
Quotes.
MPO. So it's going to use matplotlib to plot it out. So now let's hit Shift Enter on this cell.
Shift enter. Oh.
So this is what our circuit looks like. This is the circuit that you
okay.
just created. As you can see, it's a few simple lines of code. And basically now we're ready to actually work with this.
Okay. Cool.
So this has done the job of creating our quantum circuit. Now there's a bit of a step that we have to do before we can run it on hardware. And basically the way I'd like you to think about this is when you run something on a classical computer, let's say your laptop, it gets translated into instructions that the computer natively understands.
Yeah.
Let's say zeros and ones that your CPU would understand. You have to do something analogous for a quantum computer. And the way we do that is by a step called transpilation.
Okay.
So first what we'll do is here, if we scroll down, here this block of code actually retrieves an IBM backend.
Oh.
It's actually getting access to or establishing a link with this device called IBM Kingston, which is one of our Heron devices, one of our best devices. It's actually located in Poughkeepsie, here in Yorktown.
Okay.
So we've established that link. And now in this variable backend, we have access to this hardware.
So
Things on it.
this part is so like with this part now we've just established the connection to a quantum computer.
Exactly. It's
Okay.
called IBM Kingston, and yes, that's exactly right. So now that we've done that, now what we have to do is translate our circuit, like I said, the circuit that we created, onto something that the hardware will natively understand.
Okay.
And the way we do that is using transpilation, like I said, and basically it uses this function called generate preset path manager. Now, I know it's a bit of a mouthful, but its job in life is to help you do this transpilation step. So I've instantiated a path manager here against this backend that I pulled here.
Okay.
Now, another thing I'm doing here is specifying an optimization level.
Okay.
So when you translate a quantum circuit onto something that runs on quantum hardware, there's a few different ways in which you can do that. But here we want the most optimal translation. So the best possible qubits, the best possible translation into gates, so that we get the best performance out of it. You can pick a different number here, and 3 is basically the maximum. So it's going to give you the most optimal circuit that you can run.
Okay, cool.
Once we've done that, we'll run this on QC. So remember this thing that you created here,
Right.
this QC. So we do that, and if you want to hit run on this cell, what you'll see is it's actually drawing it out, and this is the result. Now there's a few things that have happened here.
Okay.
IBM Kingston has 156 qubits.
Okay.
And we're only interested in 3. So what it's done is it's taken our circuit of 3 qubits and mapped it onto IBM Kingston. What it's showing you is that it picked qubit 8 on IBM Kingston as the qubit that you would label Q2, so the third qubit. It picked qubit 15 to map qubit 0 onto, the first qubit, and qubit 96 to map your second qubit onto qubit.
Right.
The other thing it's done is it's translated this Hadamard gate into these gates. So rotations around the z-axis and square root of x gates that the computer actually natively understands. So there's a set of operations that IBM Kingston can do natively, and these reflect that. So it's a conversion of Hadamards into something equivalent, but something that the quantum computer understands. That's what we mean by transpilation. But you can see that morally the structure still looks the same, right? So we started off with 3 qubits, we're still at 3 qubits, at an equivalent set of operations, and we're still doing 3 measurements.
Okay.
So it's just been translated into something that a quantum computer can now engage with.
Okay.
This is now step 2 done.
Okay.
Now what we're ready to do is the fun step, which is running this on hardware.
All right.
We already have access to the backend. And the workhorse for this is a primitive that I'll use from Qiskit IBM Runtime. So recall that Qiskit IBM Runtime is our client for accessing IBM backends.
Yeah.
And this is called the sampler primitive. And its role in life is to take your quantum circuit and draw samples from it. So it runs your quantum circuit on IBM Kingston in this case, and then draws samples from the app. I've told it to pick 10,000 samples here. So it's going to do 10,000 shots.
So 10,000 answers from the magic 8-ball.
10,000, yes, in total, yes.
Okay.
Yeah. Now, this is what you would do to, send the job and have it run on hardware. But for ease, what we did was we kind of ran this job earlier,
Yeah,
so a while
right.
ago, right?
Right.
And we're going to actually just retrieve its results. So we have this job ID here that corresponds to this job that we sent
Right.
to the backend just a little while ago. And we'll just pull from that.
So, I mean, you did explain this to us a little earlier, but it sometimes takes a little time to run certain operations. There's a queue.
Yes. With these devices, because they're the most performant devices, there's a lot of people looking to run on them. People worldwide can access them, people within IBM, people outside of IBM. So yes, sometimes there's a bit of a queue. And for important jobs, what we try and do is get them done with when there's a smaller queue and then retrieve them later on. So, again, Qiskit IBM Runtime gives us a neat way of accessing our jobs once they finish running later on, maybe the next day or something.
Okay, great.
And that's what we're doing here. So this job is identified by this string here. Okay. And I've stored this in a variable called job ID. This is pulling my job for me. And then the results of this job are obtained by using this method called job.result. I'll run this again. And these are my counts. So it's telling me that out of my 8 possible outcomes, so for example, one of these corresponded to yes, one of these corresponded to maybe not in the initial list. It's saying that out of 10,000, 1,245 times I measured this, 1,301 times I measured this. And I want to emphasize that this was actually a job that ran on like a physical quantum computer.
Like that one over there?
Exactly. Like one over there. Exactly. But this may be a little bit harder to visualize. So let's plot a histogram of our results. And this is what it looks like. So here it's telling you that ideally, if you're in the state that you prepared, right, with those Hadamard gates, was an equal superposition of all of these states. So you would measure all of them in equal amount. The fact that we see a bit of a departure from that, and the fact that they're all not of the same height, is because of the effects of noise, and also because we're sampling from it a finite number of times.
Okay. But also, I mean, yes, there are some differences, but I guess if you're looking at it from afar, we're seeing like a pretty even distribution. So, would you say that?
Exactly.
So like the more fault tolerant a quantum computer is, like we would see lesser errors.
Absolutely. And then that's where we're headed. At this scale, there's tools that we already have that are called error suppression or error mitigation tools that you can use to reduce the effects of noise. And we have access to them through Qiskit IBM Runtime. But as you can see, even like an initial vanilla implementation where we didn't really correct for errors is already pretty close to what we would expect. So it speaks to the power of real world quantum hardware and the fact that it performs as we expect it to. Let's do something very interesting though before we move on.
Sure.
So here, remember, we sampled from these circuits and we saw the results of superposition, right?
Yes.
So we could measure things with roughly equal probability. But for our magic 8-ball problem, remember, we're only interested in one outcome, right?
Yeah.
So we have eight possible answers. We need just one,
Yeah.
right? And be done with it. So let's actually do that step here as well.
Okay.
So we're just going to sample once from it and see what it says. So let's, do you want to hit run on this cell?
Okay.
So just,
Dun.
all right. So it says try again.
Try again.
That's the outcome it picked for you.
Okay. So does that mean I need to run it again, or it's just?
It depends on your problem. So if the question you asked your 8-ball was whether your flight was going to be on time, it's, I guess, saying, well, you have to try again on another day.
So, and you're saying that this is like a very simple demo of the capacities of Qiskit, but so basically like anyone across the world can access.
So anyone can run for 10 minutes free using IBM's open plan. And, as we go on, like I said, this is a very simple example. This is actually something you can run on a classical computer. But what we're eventually headed is circuits way bigger and way deeper than this. So here we just had 3 qubits and 3 gates. For real world scenarios, for the problems of interest in solving, you need hundreds of qubits, thousands of gates. And you need, best software, access to the best error mitigation techniques, and fault tolerance and error correction as well. And that's why those things feature so prominently in our work.
Okay. I have one last question. So is this code available anywhere?
Yes. Yes, absolutely. So this specific notebook as well can be, I can have it sent to you, and I believe it's uploaded as well. So I think it was discussed in a LinkedIn post as well. But there's a more extensive set of tutorials that you have access to, that anyone has access to on the IBM Quantum Learning platform. I believe IBM Quantum Platform is what it's called. And it's tutorials on setting something like this up, or even more involved problems like chemistry simulations and so on and so forth. And they're completely free, and anybody can access them.
Thank you so much.
Thank you.